Lalit Bal. And so through him, I got a summer internship at IBM. Of course, at that time, they weren't in that nice lab in Yorktown that they have now. They were in this other little dingy facility, and the lab space was short. So I actually got my desk in a computer repair shop within the group, where somebody called Mel used to fix old PCs and put new graphics cards and sound cards into them. And I wasn't the only one. They just hired someone called Ramesh Gopinath, who was also sitting next to me. And the computer I was given was called Roukos X. It was a terminal that Salim had discarded and upgraded to a 16 megahertz PC or something. I don't remember. And that's why I got. So that's how I knew that there was somebody in the building called Roukos. And then I met him, of course. And in '95, he was here for a summer workshop, led a team. And of course, I got to know him a whole lot. I'm still a grad student, and then our association is continued. Most of the people in this room probably know Salim for his work in NLP, machine translation, Blue. And so you probably don't know, Salim is a speech pathologist. He started working on speech. In fact, when I went to IBM, he was working on speech at the time. Before that, he was at BDN and so on. So there are a few people who sort of understand how a lot of speech ideas have come into NP, and they've made the field go far. And if you start looking for the root causes, you're looking at one of them today. So Salim, I'll give it to you to tell us what.
Thanks, Sanjeev. So remembering that early 1990s, 20 megabytes was a lot of storage. So we are now 1 million times more, and we're not happy. Okay, so I'm going to give you an overview of a variety of work that we are doing in the group. I'm going to cover many applications. But I want to start with, I actually do think the title is very relevant in the sense that I believe there will be significant investment, already has happened and will continue to increase in NLP research over the next few years. I don't know how long, these things, but we probably are going through a bubble, At IBM, last year, a year ago, they started a new group, or a new division to be more precise. And that's a major event at IBM. They don't add divisions that frequently. And the focus is on Watson technologies. So from Salim's point of view, it has been a lot of fun to work on various NLP issues. And I'll just hit on some of the areas that we work with. In particular, we opened an office in downtown New York City. So if you're interested in living in the city, please reach out to me. So what is language understanding? Clearly all the work, I would say, is premised on this notion that we want the computer to understand the meaning of a sentence. But language is extremely subtle, and here are some funny examples. And I think the best one is the third one. How can a slim chance and a fat chance be the same, while a wise man and a wise guy be opposites? So it really tells you how tricky the meaning of things. And this is, to a large degree, context independent, meaning the meaning is in the phrase. A lot of times the meaning is in the context of the phrase, and that's even more subtle. And I'm going to show some examples of that. So the idea is to build systems that can construct information and map it into, for example, a structured database. Like if you had an example here in the relational database that Jack Welch runs GE, it would be nice if we had systems that can handle something that's really, really beyond our systems today. If leadership is an art, then surely Jack Welch has proved himself a master painter during his tenure at GE. So it's really extremely tricky to do relation extraction with natural language understanding. And I'm going to show some more examples of easier things than this that we need to handle if we want to really make the computer understand to some degree what's going on in a piece of text. So I'm going to give one more example before I go specifically into the technologies I want to cover today. And this is answering questions. And this is really essentially an example of what would happen if you do a question answering system based on keywords versus what's required to get high accuracy as in the Jeopardy system. So if the question is, in May 1898, Portugal celebrated the 400th anniversary of this explorer's arrival in India. If you match keywords, celebrated matches both in the question and the potential answer. May 1898, close enough to May. 400th anniversary matches anniversary. Portugal matches very well. India matches India. And therefore, you might draw the conclusion that Gary is the guy who arrived at that anniversary. Not a good answer. I'm going to show you an example from the Watson system where now the piece of text is on the 27th of May, 1498, Vasco da Gama landed in Kapad Beach. And this works because there is a date match. So the system is trying to figure out that the 27th of May, 1498 corresponds to the 400th anniversary of May 1898. So you have to reason about time, dates. I mean, it's not perfect, but you have to do something. You have to also deal with paraphrases, arrival in and landed in. There is some kind of implication. And it's not logic, right? You know, as you know, something implies this and the other thing implies the other one, you know, so it's like a little bit soft in terms of the logic underneath. But they're strongly implicating each other, I think is the right way to say it. And geographical databases is needed here. You need to figure out that Kapad Beach is really in India, so that this piece of text gets a high score of being relevant to that question. And in the Watson system, we have over 100 different features or modules, if you will, that compute and find possible answers and score them. And then you sort of put them all in a regression model to decide how to score everything at the very end. And I would say the other most important thing was the computation of some notion of confidence in the answer. The use of confidence is very important. We tend not to spend a lot of energy in it in the field, but actually as you start real-world applications, you discover very quickly it's extremely important. And I will come back to that issue of confidence at the end of the talk. So IBM has invested quite a bit in cognitive systems. We debate it. We don't know what it really means, but fundamentally it has to do with language understanding in terms of the NLP space. Clearly in the image understanding would be the related space. So there are a lot of possible applications, but the point being is that these systems will typically be systems that learn, you know, that adapt from data or interaction with users, as opposed to sort of writing a bunch of rules, if you will. So in the next hour, less than an hour, I'm going to cover 4 topics, about 10 to 15 minutes each, and I'm going to describe some and give you some demos for some of them. So the first topic is information extraction, and that's the sort of one of the key things that we do in terms of language understanding. I'm sure many of you are familiar with the ACE domain. So this is an example from the ACE domain. American Medical Association is a named mention of an entity of type organization. AIR is a nominal mention of type person, and ITS is a pronominal mention of type organization if you read the English. So the goal is to find all the mentions for a certain set of types. These are the ACE types, 5 or 7 of them, depending on which ACE you look at. And then you want to do co-reference, which means you want to group all the mentions that correspond to the same entity within this document. So within document co-reference we talk about. And then you want to do relation extraction. So chairman of its board, because you have the co-reference chain, you can infer that Reardon is the chairman of the AMA. You need one more component, which I will not talk about today, which is cross-document co-ref, which is you want to map this Thomas Reardon to a universal database where Thomas Reardon is one unique entity in the world. I'm not going to talk about it. I'm just going to show you a demo of it. So as you might imagine, we have built a toolkit that is based on statistical models. Machine learning is the key word these days. Essentially, if you have training data, you can build it for whatever language you go after. So this is our own IBM-defined news domain. We call it Clue 3 because we iterated a few versions. There's about 50 different types. Anything that's green with black font, Robin Cook is a person. So that's the color coding. And there is about 50 types. And we also have relations, and I'm not showing CoreF here, but you also have CoreF. So the relations are Robin Cook is a citizen of Britain. And the definition of what's a relation, what's explicit, what's implicit is a little subtle. But the goal is we try to go for all the relations that we can get our hands on. Because if the human can do it to some degree, quote unquote, then we would like the data to be annotated as such and hope that the language context will help the machine find the answer. Clearly, it doesn't matter what the language is. So this is the same system for Chinese. So green is person, as long as you can annotate with somebody who knows the language and are reasonably consistent. And this is the tooling that we have. We have actually invested quite a bit of effort to do a web-based tooling that's optimized to make annotation very efficient. And it's really not an exaggeration to say it's a significant piece of work. And it's been used by partners of ours, like in healthcare. They have medical systems, for coding when you go to the doctor. So it's quite a big investment in terms of creating annotated data efficiently. And this is the tool showing you in Arabic in this case. And to your right is the mention types. And to your left are the relation names. So you click on things, define mentions, click on mentions, define relations between them.
May I ask you a quick question?
Sure.
The relations.
Actually, I should have said, please interrupt me. Yeah.
The relations look very lexical to me.
Yes.
How abstract are they? And secondly, even in Arabic and Chinese, they look English. So how language specific are they?
The name of the relations are universal, right? They happen to be in English. That doesn't change.
No, yeah, but what I'm thinking is how lexical, like for example, citizen of. There are other varieties which might mean something like citizen but don't mean exactly the same thing.
Okay, so that's the trick. So we have a very detailed guideline to make somebody who is, I always say, a high school student, annotate consistently.
Okay.
So we agree on the definition of these concepts across the languages. They mean the same thing. So we actually manage our own annotation effort and the guidelines, and the people meet and agree and disagree. We measure, inter-annotator agreement. Why did you do it differently? Let's discuss it and refine. So you have to manage the annotation process very carefully.
So that's a big part of why you said it's a significant effort.
Yes.
I guess the question is, so I guess the cognitive computing group is really more about making tools that people can use to make applications in multiple domains. So
Yes.
You're not really focusing on one domain, health, or just tools
Right.
that you can actually put together.
Right.
Presumably there will be some sophisticated graphical model tools that are
Right. Right. The goal is to make tools that are easy to use by others that don't know anything about NLP. And it's all language domain independent. We actually probably have tens of domains with this toolkit. It's key that it's simple, even though annotation, unfortunately, still is a tricky business because you have to understand the notion of consistent annotation. So it's not completely, idiot-proof. So I guess you got I'm answering the question. So we have a toolkit. The key also is once you deploy a solution, you want to keep it up to date because language drifts, content drifts. So you have to sample and keep it updated on a regular basis. And most of our customers never use the advanced features. They just push a button and go on, But we actually have a very rich set of additional tooling for feature definition, but it's really not, it's only us, the researchers, who worry about it. So I want to go quickly through this just to show you what happens. So this is a piece of text. First thing, we tokenize it, which means we space out the commas and the sentence boundaries. We do sentence segmentation, that's the sentence boundaries. Then we do case restoration because sometimes text comes in a variety of random things, and we have found that always restoring case is a good thing. It tends to improve performance. Even on correctly case text, we case restore it. You parse it. Semantic role labeling for those languages where you have semantic role labeling. And if you don't have a parser, you don't have to parse it. I mean, our techniques will work less well, but if you have, then you do it. You do mention detection, which is what I mentioned earlier. So in this case, Tuesday is a date, and said is a communication event. And then you find co-reference resolution. I think I have an animation problem. So this is the relation stuff. I'm not sure what happened to the co-reference slide. It disappeared. But basically, all the ones that mention the same entity are connected. And then we do date normalization. Sometimes you can tell what the date is that they're referring to. Sometimes you can't. So I wanted to show you a demo of this system.
So this date thing seems to be a very important thing.
Yes.
The kinds of things that you do.
Yes.
The second time you're giving it as an example.
Yes. Actually, this is a case where there is no machine learning, except for the detection of the expressions. And then the whole logic to compute what it means is a constraint satisfaction kind of problem-solving problem. The reason I mention is because it's important. For many problems, you need to understand at least something about what times means and the expressions. I think I have an article here from today's news. I'm going to paste it. So I'm going to run the news domain, the clue 2. We are, it's clue 3 is the official new one, but it will show up soon. So what you can see here is green, like Strauss. Here it is. Chief Dominique Strauss-Kahn is a person, and these are the co-reference chain for him. That's yellow highlighted. Should I make it a little bigger, perhaps?
Yeah.
Okay. And you can see that Strauss-Kahn, when it's italic, sorry, the display is not very easy, but it tells you that he is located at northern France. And the way you can tell is when I highlight it, it highlights the location, if you will, and the relation name. So you can see this is quite a distance here. Was testifying at a court in northern France. I'm going to show you some example where these distances are very difficult to make the system work well. Okay, so I showed you CoreF, mentioned detection. Now I want to show you cross-document CoreF. So if I click on Strauss-Kahn, the entity in this document, it corresponds to the Dominique Strauss-Kahn in Wikipedia. So we map it to Wikipedia in terms of cross-doc CoreF. Okay.
So your knowledge base
is a snapshot of Wikipedia from, I think, like 6 months ago or a year ago, in that time frame. Okay. So I wanted to show you some examples of some errors in relations. So let me go to the right slide here. Sorry, to jump a little bit. So this is our work on English relations. And all you need to look at is the Newswire and the discussion forum data. So this is basically less formal. And the F measure, the last line of each table. Basically, we are at about 72% F measure for our set of 50 relations. And our performance on a less well-structured text is 65% on discussion forum, just to give you a number. But I wanted to look at some of the errors because I think it exposes you to sort of what the challenges are that one has to deal with. So looking at, this is the news set, I believe. And this is our error analysis tool. And what I'm showing here is that agent of is our biggest source of errors. That's 100 errors in this particular test set. So you can see that the first 4 relations account for more than 50% of the errors. So let's look at a couple of examples of errors of agent of, and they tend to be misses, right? Relation is, with our techniques, because we don't have a rich paraphrase system, we tend to miss it if we don't know it, It's right, so it's we don't know how to generalize to new things that we have not seen ever. Okay, so we tend to make.
So you're saying the lexical item that asserts the agent of relationship is not known to be an asserter of.
Yes, exactly. And so you can see the numbers. If I wanted to highlight that actually. If you look at the precision and recall, you can see that there is quite a big of. Typically, our numbers are within 1% of each other. That's something we tweak for because this is how you can maximize your F. But in relation space, it's not really easy to do that, at least with the features and techniques that we use. So I wanted to, here it is. I wanted to look at 1 and 3 and 2 and 6, because I think they're interesting. Let me make it bigger. So this is missing an agent relation, which is that the Federal Open Market Committee is the agent of the minutes. Minutes is a communication event in our model of the world. And you can read the English here. Yeah. Central bank officials believe the economic outlook, blah, 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 according to the minutes of the December 15 meeting. So it's actually minutes is the event, is the communication event. So that's a miss for us. And that's quite tricky, right? I mean, it'd be interesting to see what one can do about it. And the other example I wanted to look at was 3. So this is economist, agent of according to. So this one is quite tricky. I remember this one. So this is about the U.S. employment fell by 500,000 jobs in December, blah, 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 according to the median estimate of economists. So there is this level of indirection here.
I would say it's not economists, it's the median estimate.
Well, depends on, okay, so that's, now we have to agree on what we think is the relation here.
That sentence doesn't make sense.
Being the economist?
Yeah, I mean, the median estimate of the economist, it doesn't.
Okay, that's fine. I don't want to debate the relations. I don't want to go into that space.
No, I understand. All I'm saying is there's even ambiguity. Like, it's a bit like the classic example of a cup of tea. Is it a cup or is it tea?
Yes, but there is a pragmatic application that you want to go after. So,
in this case, I agree. Economists.
So it depends on what you're trying to. I mean, all of this is premised on a semantic. That's actually the problem with understanding. We don't have good ideas of how to build semantic models. Somebody is laughing. Okay, you're going to tell me that you can do it. Okay. All right, so I want to show you two more examples. And these are 2 and 6 on located at. So this is a trivial error. I don't really know why we made this. I just saw this yesterday, so I will have to dig into this one because this is trivial. Gary Townsend, Chief Executive Officer, comma, Hill Townsend, capital. But we just missed it, okay? Because a little bit odd lexically. And I think I wanted to do 6 also. This one is actually quite tricky. This is about, we missed that the Black Mesa Barbecue is located at a crossroad, which is located somewhere else. The Black Mesa Barbecue gas station and lunchroom, home to the 3 generations of the Maples family at a lonely crossroads in the eastern Arizona. So it's very far. Yeah. But we humans understand it.
Do you know if in this example it misunderstood the location to be eastern Arizona?
No, these are both. I'm sure we got correctly, since it's not displayed here, that the crossroad is located in East Arizona. So we do that chaining. But we missed the first link of the chain. Okay, just I figured I want to show you some errors of relations because it's a very challenging problem. And to close on this topic, I wanted to go to parsing a little bit because that's another weakness that we are investing quite a bit of effort in, which is, as you know, everybody, you probably don't know, we pioneer statistical parsing. And people have been working on the same test set forever, and people think we're making progress on parsing. And in reality, if you look at parsing from the point of view, how well do you do on conjunction structures, which is really very important when you're trying to do machine translation or language understanding, you'll discover things haven't moved a whole lot, They moved a little bit, few percent. So right now, while we claim 80% on OSU Journal, 89% on Ontonode's test sets, doesn't matter what the details are here, the conjunction is twice the error rate at 80%. And it's very disruptive when you screw up the conjunction because the whole thing becomes, in machine translation, the output is not meaningful anymore. And relations also are critically dependent, I think, on parsing. Even though our techniques don't require a parser, but it makes a difference when the parser is available and does a good job. So this is a silly error that we still make in conjunction. The sentence is, where is my mouse? Here it is. The joint PAOMIA accounting command or JPEG. It's a very simple conjunction. So obviously the thing on the left, on your right is correct, which is the joint PAOMIA accounting command is the conjunct to JPEG. But our system, unfortunately, is completely screwed it up. That's a simple example. I have much more trickier examples, but I don't want to spend time on them today here. Okay, now I'm going to talk quickly about machine translation. We've been working on this problem for a while also. We distinguish between the 3 use cases: text to text, speech to text, where you do speech recognition first and then you translate. This is for closed captioning programs, for example, and speech to speech. And I'm going to give you a demo of speech to speech. It's all premised on a parallel corpus. And the importance of a parallel corpus is that you can customize to a new domain efficiently. If you have parallel data from a new domain, it makes a big difference for the quality of the MT for that domain. And I'm going to show you some examples of how we use customization. I also like to show this slide a lot because this is progress over the years. Machine translation is one of those areas where progress has been steady, and everybody tells me it's going to saturate next year. So this is Blue scores from March 2002 through 2007, TIDES program. This is H-TER score, lower is better now, for the Gale program. And this is another automatic score, which is the average of TER and Blue on Chinese, lower is better. So you can see things have been improving continuously, and that's really quite an accomplishment, I think. I think DARPA is making a mistake, but that's a separate discussion. So we have many systems. We build systems that are, phrase-based, a richer phrase-based, which I will describe in a moment here, and tree to string, string to tree, forest to string. So all possible combinations you could imagine we are playing with. Our best system for Arabic is this model, which we call the direct translation model. Basically, it's a special kind of phrases. It's like a very simplified hierarchy rule, if you will, with lots of parameters. A huge statistical model that says, where is the position of the next source word I want to translate? And I can translate it with one word or two words or whatever thing I want to translate to. And what is the possible translation for it? And you have a lot of features. We have, I think, tens of millions of features that are built as a big Maxent model to predict the probability of this path in the decoding. And I want to show you something that actually is very useful from a pragmatic point of view. So if you try to translate Arabic into English, like using online systems or other systems you have access to, you'll discover that typically in Arabic, they will say, he visited a number of bakery owners. And the he is spurious, because in Arabic, they tend to start with the verb. But in English, we don't start with the verb. So this he comes out of nowhere. If you add the parse structure to the features that decide what happens next, so here the parser, the Arabic parser, which is shown vertically, so you have to get used to this way of looking at things. There is a verb followed by a NP subject phrase, which is from position 2 through position 5. So if you have a feature that says, I've translated the subject phrase node, where should I translate next? That will put a high probability to translate the verb next. That will make the translation system translate the subject phrase first and then put the verb. And then you will get output like this one. A number of bakery owners visited the supply managers. And that's actually one simple sort of linguistically motivated feature that makes a big difference on performance. Now, this relies on having a reasonably reliable parser. So this stuff works well for Arabic. It doesn't work as well for Chinese. Our parser for Chinese is not very good. So there, forest to string works better. But that's disappointing, as you will see in a moment, because the final output is not as good as this system. We still make silly errors, right? Like the word the is replacing if a word that means regions or regional. So we still have these content word deletion problems. It's very hard to solve this problem. I mean, if you work on MT, look at the errors of that type and see if you can fix them. All right, so we compared our system. This was last August and May, depending on whether it's the Arabic or the Chinese evaluation, to an online system. And you can see that we are quite a bit better than the online system on news text, both for Arabic and for Chinese. Now, it's very hard to compare human judgments across languages. So all you can compare is the relative of two systems. Don't draw any conclusions that the 288 up there is the same as the 281. Actually, it's day and night difference. Just that different judges have different scales for what's good. We've discovered this from the days when we discovered blue. The Chinese evaluators were very liberal. So let me show you a demo of the system, and then I'll walk you through this example just to illustrate some things. So this is the Arabic-English machine translation system that I just described very high level for you. And I'm going to go, I assume my connection is still on. I'm going to go get a web page from the Arabic BBC. Yes, we are in business. And when it becomes black, we would have gotten the Arabic page, and now it becomes English. So we can read, the United States confirms hostage killed Kailash Muller. The killing of an aid worker Kailash, is that her
It's
name?
Kaila Muller.
Kaila. There is no Ash. I was saying it doesn't sound right to me. Muller. Okay. Al-Assad, BBC, receiving indirect messages from America about the raids on the organization of the state. This is a common error I have noticed. The state is ISIS. Because in Arabic they say the state now. They changed their name. At least in newspaper reporting. So this is actually a good example of, I mean, if you read the English, it's really good. Let's look at a paragraph just so that you can, I convince you that this is really good. Let me make it a little bigger. In an exclusive interview with the BBC, Syrian President Bashar al-Assad confirms that his government received information from the United States through a third party on the air raids against regulating the Islamic State. So it's like, 95%, I would say, accurate. Okay. So this is Arabic. I was going to make a comment about this. I feel Arabic has become good enough that now we can start worrying about pronouns and more subtle word senses. Like the state translation here is a word sense thing. And it's probably worth trying to figure out how to make this work for real, because the system is good enough from a structural or reordering point of view. But I want to show you Chinese, which had the same score. And you will see Chinese is about 5 or 6 years behind Arabic, I would say, from a quality point of view. So I'm going to get the Chinese BBC page. And Chinese, it's only 50%. Every other sentence, you will get the gist of what's being said. That title is not very good. But as I said, 50%, I get a second chance. Assad, Syrian air intelligence learned from the third party. Okay. So Arabic used to be like this. Okay, so that's why I was saying DARPA may need to rethink a little bit about solving Chinese. Okay, I think I had already highlighted for you the verb position thing in Arabic. So this is an online system called National Support, whereas in this case the subject phrase is very long. The National Alliance to Support Legitimacy, supportive of the Muslim Brotherhood group in Egypt, called on his supporters. So the verb can move, 15, 30 words into the sentence. They tend to be very long phrases in Arabic. And doing a good job at reordering allows you to understand things. So like in this area here, head of bayonet in Marsa after the overthrow of massive popular protests, the spearhead in ousting Mercy after mass protests. So getting order is very, very important. That's why I think investment in parsing is also worthwhile. I'm going to go quickly here. So the discussion so far was on news. You can do it on more informal discussion forum content. And clearly there, the systems that are trained on more informal data tend to do better than the general purpose online systems. So the difference is really huge in terms of the human evaluation.
Salim, you can tell us what algorithm.
The devil is in the detail, I gave you a hint. The hint is fundamentally feature engineering using linguistic structure, going after certain specific problems that you want to solve next. I mean, to get into the nitty-gritty, algorithmically it's trivial. It's a Maxent model, right? And it's really fundamentally good linguistic processing. We add, various types of linguistic processing. I didn't talk about how we deal with Arabic. So Arabic, an important thing to do very quickly is to segment it so that the number of words in the new Arabic equals the number of words in English, because the concept of a word depends on your target language. So there are lots of, yeah, it's linguistic engineering to put in the right embedding, and then feature engineering along the way. And if your componentry is accurate enough, you can be more aggressive in your models. If your componentry is not very accurate, you want to do more of the forest to string type of things, which are not as rigorous. They merge hypotheses that don't mean anything, together into one hypothesis.
And so this feature engineering, are you doing it using human insight, or you're making machines figure it out?
I wish. Okay, so all this work I've described to you here has been by human insights and guesses. There is clearly a lot of excitement about neural nets these days.
Yes.
Let's wait and see how well they do. I'm serious. Because you discover very quickly when you talk to people who are doing lots of neural nets, they are starting to do feature engineering using a very complicated beast for feature engineering. Sorry to show my bias.
You said that it seemed like you described the maxent model for
Yes.
scoring a particular transition. Right?
Yes.
There's still a search, like a beam search. Here.
Oh, yeah. That's, yeah, search is key here because it blows up very quickly in your face. And actually, I hate to admit this, but we cheat. It's not a pure maxent model. That's one component with a weighted bunch of other things that you score together, right? So you always have to do what I think of as system combination, which some people call, probabilistic discriminant models by tuning some weights. Yeah, so you have to have both. But the maxent model contributes. It's a useful component to have in the mixture of things. I'm sure you guys know more about this than I do. Clearly, with Arabic chat and SMS messages, it's a much richer problem in terms of how people think what a word is and those kinds of things. So I'm going to go quickly. We have been sort of pushing the research agenda from a machine translation point of view, but we also have done a number of applications of machine translation at IBM. So we have done systems with customers for patent translation. We have deployed MT within IBM for helping the human translation business of IBM. And I'll show you quickly what some of the things we've done there. And we have a server, that you can deploy as a customer. And we do about 30 language pairs. And you do the usual, web browsing I just showed you, chat applications. We even have a Watson system where you have MT on the front end. So you can have multiple languages supported by an English Watson system. So in the remaining 20 minutes, I want to cover a little bit about some recent work we have been doing on speech-to-speech translation. The idea being that you speak in one language on one side, recognize it, translate it, go synthesize on the other side, except you want to add a dialogue manager so that you don't translate before you're confident that you understand what the speaker has said. And there are, for power users, those who want to learn some commands, now it's a conversational system that the user can use to edit and interact with the system to fix up, so to speak, the sentence before it gets to the translation side. I'm going to skip this part. So one of the key things in this system is we do OOV detection, detecting that the person has said a word that's not in the vocabulary, and then interacting with the user to learn this word. And clearly, it uses features from the acoustic space and the language space, the content, the sentence. And clearly, we use a confusion network because when there is uncertainty, chances are it's probably in OOV, particularly if the other alternatives are what we call fragments, which are engrams on phones. So it's not other words, but it is engrams on phones. Then the likelihood of it being OOV is much higher. And the other thing is, actually, neural nets have done a huge win on speech, unlike on translation or language problems. And this is a demonstration of some of the results. So our BOLT 2012 was state-of-the-art Gaussian mixture system. Our 2013 system is a convolutional neural net. And you can see the error rate on your typical sentence speech-to-speech drops from 14% to 7.5%. That's really not all due to the neural nets. I would say about half of this improvement is due to the neural nets. The other half is, lots of other little things. And you can see it's uniformly useful for spelling and for commands and other things that what we call the cache. And now all our speech ecosystems are clearly CNNs and DNNs. So this is an example where the person said, but to survey it airily, and that's an OOV word, and this is a real example here. It got recognized as hairy Ali, or hairy early, or these fragments, triphones in this case. It can be from 1 to 5. So clearly, the red region is probably in OOV. And we can measure OOV rates. So we have these curves, which is you don't want to declare something as OOV when it's not OOV because it creates an interaction. It's expensive. So the detection rate is about 80%, and the false positive rate is about 5%. That's sort of the operating point. We don't want to be higher than 5% false positive. And we improve the features. So we are basically now at 5%, we are really 80. And we even, for the operational system, we move it to the left, we're closer to 3% in terms of our operational point. And you can see that the enriching the features improve. So we started with the red curve, which was based on the Gaussian models. Then with the CNNs, things improved a little bit, not dramatically, but improved. And then adding more richer features, another Maxent model gave us an additional boost, at least in terms of recall rate, detection rate. And this is on Arabic. The previous results were on English because you have to do it on both sides. Arabic is a little worse. We were in the 80s, whereas here we're more like in the 70s, 60s, mid-60s. So it's tougher on Arabic.
Typically, what are these OVs? Are half of them like proper names or?
It depends on the year. So it's a mixture of half names and half OVs, because this task is artificially constrained by DARPA and NIST. Right. So it's the trans-stack task. So it's only that vocabulary. We're not allowed to add any additional words. So it's about maybe 50,000 words, 60,000 word vocabulary on English. Okay. So there will be a lot of non-names OVs also.
Okay. And because it's Arabic, do you see inflectional form OVs, or you just expand the vocabulary big enough that?
No, I mean, we do expand. So the notion of prefixes and suffixes, right. So that doesn't count against you in terms of definition of vocabulary. Right. But still, I would say the largest problem is really, actually, I don't know about Arabic, so I don't want to say. I don't know enough about the statistics of what the errors are. I don't really know.
What do you mean you replace the CNNs by?
CNNs?
I mean, you still have some even much models there.
Yes, but
you don't see the pictures between them and the
correct.
And you keep the same number of features?
No. Okay, I don't remember all these details. I don't do this work, right? But I would say that's never our goal from a bottom line point of view. I'm giving you now here bottom line results as opposed to comparing incrementally the different things. Yeah. The only constraint is the training data is the same.
Right.
So it's up to you. Plus, I don't know what it means, right? I mean, number of parameters is a very misleading concept. Yeah. Okay, so I wanted to give a demo just to show you, So this is I think I should reload just because we switched things and maybe that it doesn't quite is in the right state. So we had a 7-day evaluation at DARPA a week and a half ago. So I enjoyed my life for 7 days. And we have a system where it's only hands-free, eyes-free, which means only a microphone. And we have a system where you have a tablet, if you will. But today I'm going to show it on the computer. Good morning. My name is Sakrajda. Can you tell me what happened to the truck that was parked next to the school yesterday? Hope it works. I should get a microphone. Okay. Something happened. The rest of the sentence did not come up, but it detected that probably this yellow region is an OOV. So I can basically click it's a name. It should prompt me. Why is the audio not working? Do we need to raise the volume? But you can see it told me, please repeat the name. So I'm going to teach it a base form now. Sakrajda. Okay. Can you get volume?
I'm raising it to see what it does. So far, no luck.
Okay, that's fine.
Yeah, okay.
So I'm going to say translate. Or maybe I'll start over just to show you, because I'm not trying to do a dialogue here in Arabic. I just want to show you some functionality. Good morning. My name is Sakrajda. And I was wondering what happened to the person we brought yesterday who had a fractured leg. I should use a real microphone, you know.
Click on translate.
It didn't recognize Sakrajda. It didn't learn it very well. Okay, so I said we. So the confusion network gives me an alternative.
Incorrect. Click on translate.
We brought yesterday. I'm not sure what this is.
Who had a fractured leg?
Who had a fractured leg?
Who had a fractured leg. I should really use a microphone, but that's okay.
Incorrect. Click on translate.
It didn't work. It's who had.
It looks like a limit on how many words it can have.
No. But it's not recognizing very well.
Incorrect. Click on translate.
Oh, it recognized it to Sakrajda now because it's more confident now. It was not confident earlier. Okay, so I can translate it, but I'm not going to translate it because you don't know Arabic, most of you. Okay, so what you have here is OV detection, error detection also. The distinction is a subtle one. Name detection also, and alternatives for regions that the user can click on when there is a screen.
So do you want to say a few words about what's the difference between OV detection versus error detection? How do the models work underneath?
Right. I think the fundamental issue is if the statistical model says it's a name, then we will tend to decide it's an OV.
Okay.
That's the fundamental feature that makes a difference. Otherwise, there is no... Acoustically, you cannot tell. But we can predict sort of, chances are here we expect a name, and if it's a name, the odds are it's an OV. It's context, linguistic context, word context. So DARPA evaluates us, right? And they measure number of translated adequately, and we did well last year. We're waiting for the results for this year. We don't know how well we did. Okay, I want to finish with one more topic, which is uses machine translation to speed up human translation. IBM spends quite a bit of money. They translate about 400 million new words every year. And they do it with how many vendors? 115 suppliers, and they probably have thousands of translators. And their goal, obviously, is to reduce the cost per word. It makes a big difference for them. And they were willing to try us. They had tried machine translation in the early 2000s. It was not very successful. But they were willing to try again with us in 2010. And they were very nervous, right? Because we don't want to make things not work in a production environment, because this is not like in a lab. It's really the real production, real people out there. And they talk about exact match. So if you have a sentence like you want to translate Hillary Clinton in Mexico, and you have something in Francia, you only have to change one word. So that's called a fuzzy match. It's close enough. You click the fuzzy match, and then you change, edit, post-edit one word. And if you have MT, maybe it's perfectly good. And it can be more complicated. Let me not spend time on this because I am running out of time. So it takes time to process whether the fuzzy match is good enough or the machine translation is good enough. So this issue of time is very tricky. And this is the tool. And essentially what we did is, for every document that IBM wants to translate, we build a customized MT. Because typically for IBM documents, they've had previous versions of the product. So there are related the previous version of the manual. So you can have a very good customization corpus. So we do document-specific MT. So when a document comes in, we have the history, we search and find all the previous translations of that of related documents, Use that to create a special corpus, build a customized MT system, and that's what we do. And then we translate with that customized MT, and we ship it to the humans. And it was a project where we had to be production, right? 1 to 2 day latency, and we handled, 16 human translators, about 4.5 million words. And these results I'm going to show you are 1,700 person hours of work. So this is a lot of humans doing corrections.
So when you talk about the document-specific corpora, the first instinct, of course, is to find documents which are very similar to the source document.
Right.
But we also then think about complementarity, meaning once you find those, the next one you find, it's not
Yes.
helpful if it's just a mere
Yes.
duplicate of the first.
Okay, I don't remember all the details, but we worried a lot about this issue of how do you rank sentences when you do corpus-specific selection.
Right.
I don't remember all the results. It's not a huge win, otherwise I will remember it. Okay. We did this a few years ago. But here, in this project, we take everything. It's too expensive to do the sentence-specific selection. Okay, so we measure on millions of words, and we measure under two conditions. When there is a fuzzy match present, which means the sentence is close to something that was done before by a human, that's the region where most people think MT cannot help because you already sort of have something very close. And the case where there's nothing close, we call this no proposal, where they have to do it from scratch. And you can see that for Spanish, in 2010, the humans liked the MT enough that they used it 53% of the time as their starting point. So they were voting with their fingers. Now, they do not know if they are faster or slower. They think they are faster. Okay? But this was very encouraging for us because they liked it, because we were very worried at the time, because if they hated it, then the other management would not let us keep going, you know? Then we measured their speed. Let me go to the punchline. So if they do it from scratch and it takes 1 unit of time, if there is a fuzzy match without MT, they will do it 30% faster. They will do so many more words per unit time. But if MT is present, even when there is a fuzzy match, it's even faster. So MT is giving 31% speed up when there is a fuzzy match, and 41% time speed up when there is no proposal. So this is a huge win, you know, because that really reduces cost. You know, these people are measuring productivity in the few percent, you know, 10% is a big number. And we did a pilot. We have it now in production for 5 languages. Actually, now it's more 7. This is an old slide. But the most critical one was Japanese. So this is where I want to spend a couple of minutes to talk about confidence. So in Japanese, the humans were using MT. So they were using it, you know, 33% of the time. But in reality, they were slower. They didn't know that. But they were actually slower. So it was not a good solution, because so it's not enough for us to get them to use it. You know, they have to be faster so they can make more money. You know, so it's a win-win for us and for them. So this is where we realized that they were spending a lot of time reading the output, the options, and that additional reading time was too expensive. It was not leveraged enough by the post-editing effort to compensate. So it would be useful if you had a confidence measure to tell them when to look versus not to look. Then you can achieve a bigger win. That's why I was saying earlier, confidence is very important when you come to the real world. Because then if you have a notion of confidence, I'm going to go quickly here, I'm not going to tell you how. But basically, you need to do document-specific confidence estimation as opposed to generic confidence estimation. Okay? And you get better results. You know, the correlation is more like 0.53 versus 0.1. And it leads to efficiency now in Japanese. So even Japanese now is actually faster to use MT than not to use MT, because we tell them when to look at the MT. We always display the MT, but we tell them a grade, A, B, C, and they have to learn that look at it always when it's an A. You decide if you want to risk it on the Bs. You don't want to look at the C unless you're looking for a fragment. So sometimes it is helpful for them, even though they don't want to use the whole thing, to use a fragment, because they're looking for a phrase, they don't know what it is. And this is more detail of this. Let's not get into that. So this is it, I think. I'm almost on time, actually. Oh, no, I have one more topic. Actually, this is the one I need to publicize. So IBM Watson Group has been deploying a lot of cognitive applications and tools on a cloud. It's called Bluemix, is the higher level cloud where you can see a lot of other things. But if you want to focus on only cognitive applications, there is something called Developer IBM/Watson. And if I click on this, and I want to take a minute or two to talk about it, because this could be useful for you in terms of projects, because you can have access to some NLP tools that you can use in interesting ways. And to get quickly to the right place, there is a demo place here. So I'm going to go to the demo place. Just, you know, you can look at this at your leisure. But for now, let's quickly go to the demo place. Here it is. So there are about, I don't know, 15 maybe now? How many? 8 plus 5, 13. 13 services. So, and they have, let me walk through a few of them just to do some high-level summary. User modeling is a system that analyzes somebody's tweets and give you personality traits of that writer. Concept insights, it has to do with getting semantic equivalent of meaning of phrases and things of that type using a Wikipedia-based semantic model. Concept expansion, I don't remember what that is. Yeah, this is like a vocabulary. This is like a system that can learn a vocabulary for drugs, medications. Language ID, you know what that is from text. Machine translation, the demo I gave you is accessible from here. Message resonance, if you want your email to resonate with a community of people, it would suggest words to change from your text that has the same meaning but is more associated with that group. Question answer, as you might expect. Relationship extraction, that's the SIRE toolkit I mentioned to you. Speech to text, I gave you a demo, right? This is English only here for now. Text to speech. And then some additional stuff, including the image, visual recognition stuff, which is associating concepts with images. So it's a Bluemix environment, which is a flavor where you can build your own app. So if you wanted to build an app using these technologies as is, you can quickly build an app, in half a day, right? But also, if you want to do something more sophisticated, you can do something more sophisticated using these building blocks. And it will be part of the slides, the URL. If you type what's on Developer Cloud, you'll find it.
By the way, over this weekend there was something called Hot Hacks here at Roukos, and there was at least 4 teams actually using the in fact, actually, IBM has completed a dedication award.
Yes, thank you. That's great. Yeah, I'm not surprised. Actually, IBM. Yes. Is IBM? Yes. Is IBM giving a course on Watson here or no?
No.
Because they are starting to do courses at universities, and there is interest. If there is interest, we can discuss offline, because they're very motivated to train as many people as possible in cognitive technologies. Seriously, they're looking for people. Oops. Okay.
Thank you.
Okay.
Answered all of them on the day.
I guess.